I'm gonna talk about self-similar solution and their properties. Our main object is diffusion process, which obeys the first and second law of Fick. According to first law of Fick, flux proportional to concentration of diffusion. And according to second law of Fick and transport equation, we can come up such type linear heat equation. Application of nonlinear diffusion arises different areas such as porous medium equation, filtration, groundwater dynamics, movements, non-Newton fluids dynamics, heat conduction, also include this reaction diffusion process. Also, we have image processing with parabolic equation profile. Also applying such type equation to population dynamics, we use Fisher-Kappa type. More general case, the linear law of Fick's doesn't work. So we come up with Ostwald over law with such type form. If there is m equal to 1, we can encounter Newton fluid. In the other case, it's describing non-Newton fluids behavior. From this law, we can come up with parabolic Laplacian equation. There is p equal to m plus 1. And it also includes such type of partial case. One of the central problem in diffusion equation is porous medium equation with such type K function. There are encounters new properties such as finite speed of propagation, free boundary line, and so on. It also includes a Leibnizian and masked equation in particular case. When m is equal to double 2, it's describing isothermal process, and when m greater than 2, it includes adiabatic process. More partial case also includes groundwater flow, movement, and plasma radiation. And there is a few fields of solution exploring. The first one is a classic solution. Next is limit solution, but we consider more weak solution. In other solution terms. Our main question lies about global solution or finite type blow up. definition of global solution and blow-up solution. If U is always less some finite numbers, we say this global solution for all t time variables. Different kind of approaches included by first work, Kaplan, including such type of energy functional using by eigenfunction and a given value. Second one is Fujita's work, and there is most important critical exponent lies. It's so-called critical Fujita exponent. It's separate only blow-up solution, and both global and blow-up solution depended on how small initial data. The next one is introduced by Levini, using by concave properties of such type of function. Second important critical exponent is this indeterminate initial data, how can be small or large. Now we're moving about of self-similar solution. There is some kind of self-similar solution form exists. In general, is described by 6 equations. In particular case includes with such type form. The first one describing especially for global solution. The second one describing more blow-up and maybe included extension if power of the minus the variable positive. We have also exponential form of profile. And we can choose the power of t by such type of rules. We need to remove all t variables and transform our equation from PD to ordinary one. So for this model, or this case, we choose alpha and beta such that we can see here alpha or beta dependent to each other, not exactly values. So second condition we can find using by energy conservation law or initial mass. So m is constant, then t power of t must be constant too. In other words, alpha plus n multiplying beta is equal to 0. So we can find using by this two conditions the value of alpha and beta. We also consider the most important works behind these solutions. The first one is the Cauchy and company's work. They studied thermal waves of heat process. The second one is parabolic works, the most important work. We also call it this form of solution, parabolic profile solution, which includes such type denotation. We can encounter here finite propagation, which tells us how process moving, especially it's some domain. The next one is Pattle's works. It's included diffusion process via Gaussian fundamental solution. We can also find such kind of alpha and beta values for p-Laplacian. More comments about behavior profile. Why we consider self-similar solutions if they don't or didn't provide existence or uniqueness of the solutions. So that's why solution converges to parabolic type or source type solution when the tends to infinity. The second one is stability. Our main works is p-Laplacian, but with density functions and non-divergence form, which describing by u power q. And here we state some initial conditions for parameter. We can also find such types, two exponents. The first one, Fujita, and second critical exponents. If such kind of conditions satisfied, then we have blow-up solution, infinite time. If we introduce a new variable so-called v is equal to u with power of 1 minus q, then substitute this into our main equation, we come up such type force equations. And we can apply our self-similar approach to these equations. And we find parameter of alpha 1 and alpha 2. After this, we obtain Seven's form of ordinary solutions, and we look solutions with initially and bound initial conditions, and also include this boundary. The second case is slow diffusion case. It includes parabolic profile in the form of NUUz. If such conditions hold, in other words, when n1 is smaller than minus n and beta 2 larger than beta 2 critical, beta 2 critical is Fujita. And then we have solution estimate by upper, and also have free boundary estimates with such type form. The next case, we have fast diffusion. It's occur when M2 plus K2 multiplication is minus 2 is smaller than 1. There is also parabolic type solution, but we have plus instead of minus in function g. So in this case too, we estimate our solution to the problem 1, and we take such type estimates. Also, we may encounter a critical case which occur our main parameter is equal to 1. And in this case, we take a solution with a Gaussian function or exponential. In this case, we also take estimates to our solutions for the problem 4 and 5. So our introduce parts also have we also did numerical calculations based on the iteration and Samarsky-Sobel scheme. After applying these schemes, we use by straight diagonal algorithm or Thomas algorithm. And we get such type of graphics of our self-similar profile solutions. The first one is given by main parabolic profile solution. The second one is occur when our main parameter smaller than 1. It's responsible for fast diffusion case. It also have a different kind of graphics. The partial case of numerical parameters m, k, p. The next problem states as follows, but there is also included third density function. We talk about of numerical schemas in such kind of also graphical representation. The next problem is stated as follows, and we consider third density function. In this case, we find critical exponents Fujita and secondary. We find of when blow up occurs infinite times. In this case, we get also global solutions estimates, but with new conditions dependent on our inequalities for fast diffusion case 2, and the critical case, which includes Lambert function, in this case, we also encounter with another critical case, which depended on alpha 1 and alpha 2. In this case, we also take estimates of solutions with profile of natural logarithm. There is have another estimates to our solutions. This also includes numerical calculations. For slow diffusion case, we have figure 1, and there is, we may say, some kind of interval which characterize of how spread our process domains by x of horizontally moving, when the variable of time increasing, our interval becoming smaller. We also studied system case with such type of equation. There is different kind of systems we may encounter, but 21 is so-called crosswise diffusion, which depended on power of second system variable v. For all case, we get estimates to solutions by different kind of approach. We also have graphical representation for such type systems. The first columns describing U and V together, and second and third. Each one separates with each other to compare how their values grows or decrease. And also we come up with such type conclusions.